Hello everyone, thank you for joining here for my presentation. I'm Beleswar. I'll be talking about early boot and late attach of remote processors for time critical applications. Huge name, but we'll try to break it down part by part. So a little bit about our company. TI believes in upstream first mentality. We work with a lot of open source communities to develop long-term sustainable products, and we have this ingrained value to give back to the community via code contributions. A little bit about the speakers. I'm a software engineer in the Linux core product development team. I work with upstream U-boot and Linux. Outside of work, you'll find me fiddling with open source security projects. I'm a security enthusiast. I also have with me Vaishnav, who is a senior software engineer, works with the same team. He's also a maintainer for TI platforms in Zephyr RTOS. He's attending the conference virtually. So let's start with the overview of the presentation. First, we'll see the background, like what we have the boot flow currently in the Linux kernel, and we'll establish the problem statement. Then we'll jump to the solution model. And before going into details, we'll just look over the basics of IPC so that we can relate to contents better later. Then finally, we'll jump to the crux of the presentation, the early boot and late attach model. Here we'll discuss about how the framework supports it, and what are the challenges in this model, and everything you need to do as a vendor to migrate into this late attach flow. Finally, we'll close this session by talking about the best debugging lessons that we learned, and it will help you if you are trying to migrate into this flow. Right. So basic slide. Why do we have so many CPUs in our heterogeneous SoCs? This is an example of a AM64 SoC Ti. It has around 7 cores. We have 2 application, 4 real-time, and 1 isolated core. So it's just to maximize the efficiency of the SoC, right? So some cores are designed to handle specific use cases, like your Cortex-A, it is an application core used to run your HLOS. Some Cortex-A real-time cores used to run safety-critical software, time-critical software. We also have DSPs, which are useful for complex image or video processing. So the whole idea is to have so many processors so that you can offload the control from the application processor to this remote processors to maximize the efficiency so that your application processor is free and doing other things. So for all of these, of course, IPC is very important, which is basically inter-processor communication to talk between all these processors for this kind of efficiency. For the background, so this is the default boot flow of Linux when it tries to boot a remote processor. So when it comes up, it identifies all available remote processors and then boots them with the firmware if it is available. So you can see we start with the ROM code, then we go to the bootloader, then it hands over to the kernel, and at some point your remoteproc drivers get probed in, which then identifies the remote processors and starts its boot. So you can see this is the time that takes to boot this remote processor, which is exactly what we are trying to reduce. So here we arrive at the problem statement. We need to have a fast boot of these real-time remote processors in the SoCs. If you come from an automotive background, you know those requirements are really time critical. You want like early display or early splash screen, early audio in milliseconds. So, and all of these are safety oriented as well. They need to be run on specific real-time safety cores like your Cortex-R5. And these are complex as well. So it's not like your remote processor is just doing an early splash screen and setting isolated. It has to do a lot of complex things together to complete the requirement. Like, for example, if it's doing an early camera thing or displaying a splash screen, later it also has to do a 3D surround view, support a 3D surround view, and for that it also has to do this image stitching. So it has to take captures from all 4 cameras, then talk probably with the DSPs to stitch those images together, then talk with the GPU to render that 3D projection of the entire stack. So for all of these complex requirements, the MCU needs to talk to various on-chip peripherals. Similarly with early Ethernet is pretty simple. You do Ethernet initialize early, but the firmware also later has to support the Edge AI IPC stack. So for all of these, it's not just sufficient that we boot it early from the bootloader and just sit along. So you'll have to also support a kind of a attach case here so that we can support these complex requirements. If you talk about a very optimized Linux boot, it will take you around 1 second to complete. But the requirement for automotive early audio chime and all, it's like 200 milliseconds. So clearly, we can't wait for Linux to complete booting and then start the remote processors for these critical things. So wherever the solution, it is called the early boot and late attach model. What we do here is we boot this remote processor early in the boot stage through the bootloader, and then we attach it to the remote processor late in the kernel stage to set up IPC, because kernel is a IPC master. I want to stress here that both these stages are equally important. Your early boot supports your handles early requirements like early display, early audio, all of that, while your late attach also handles complex use cases, like if you want to talk to your GPU or your DSPs, other processors. All of that is only enabled when you do a late attach to the processor. Right, so if you see this early boot, this is what we had. If you see early boot, we started early from the bootloader, and the time now we have saved is so much, which is very efficient in automotive systems. So let's see a quick video about automotive use cases, how late attach early boot is getting into picture. You can see this is an early splash screen demo. We have a splash screen coming up in milliseconds even before your HLOS has completed booting. This is where your Linux comes up and takes over the display. Similarly, for early RVC, we see the camera buffer very early, even before. This is when your Android is booting, and still it is booting. So we have these are all early boot requirements. Now we'll see how late attach also comes into picture and helps these requirements. So this is a rear view camera feed, right? So this is early RVC, that is pretty simple. But if you see sometime later, we also need to surround a bird's eye view in the right side. So here it needs to get camera frame buffers from all 4 cameras, and then talk to the DSPs to do image processing, image stitching, talk to the GPU to render this 3D projection. So for all of these cases, you want to set up IPC, and for that, late attach is very important, which is also very complex to support. We'll see how the framework supports that. This is the same demo in a different surrounding, so I can just move on. Okay, so before we jump to the main topic, here is some basics of IPC. So typically, if you want to boot a remote processor from a host processor, what you want to do is you load the remoteproc firmware, and you allocate all resources required by the processor before starting it. So now the question is, there are so many OS. So there is Linux, there is RTOS, flavors of RTOS, there is QNX. So there needs to be a common standard in which the remote processor can advertise that all of the resources that it requires before powering on. That is taken care by this term called resource table in Linux. So it is a common standard where you can define the resources that is required by a remote processor. And this is part of the firmware image itself. And since the implementation is common in both Linux and firmware, when Linux loads the firmware, it can identify the resource table out of the firmware image. So it has all these metadata, and finally it has an array of offsets which points to the various resources it requires. Coming to the types of resources, currently we support only 4 types of resources in Linux. So first is the carveout. Pretty simple. If your processor or your firmware wants some sort of this device address and this physical address of this length, it can advertise that fill up these basically structured objects. Similar to that, we have a VirtIO device. This is very important to set up IPC. So each VirtIO devices would have typically 2 V-rings. V-rings is nothing but circular buffers, you can think of that. And 2 V-rings because one will be used for TX, the other will be used for RX. And we have a V-ring structure which would have more details like this, like what is the physical address, what is the device address, and the length of the V-rings. And then it has also the mapping type of resources. So if your firmware needs it is behind an MMU or stuff like that, you want to map some sections of memory, some sections of device address to physical address, you can do that here. You can mention what are the sections that you want to map, and Linux will do that for you. Finally, we have a trace buffer. So this is pretty helpful in debugging. So what you can do, so firmware, whatever logs it wants to put, it can put in this buffer, which you can attach to the kernel debug.fs and then read at runtime. Now coming to the notification. So after, how does the firmware know that Linux has allocated its resources? So Linux does that in stages. So first, when it finds a VirtIO device in the resource table, it will write this byte into the status field in the resource table in the memory. So which is also this part of memory is also readable by the remoteproc. So it happens in sync. And then whenever it finds a matching driver for that VirtIO device, it will write another byte too. And then when the matching driver probes has completed and has done all the V-ring allocations and all, then it will finally write 4. So if you add all this, that will be 7. So your status byte would have 7 when Linux has done this allocation. And finally, it will send a mailbox message or some sort of interrupt, whatever you use for interrupts. It will send it to the remote processor saying, hey, I've allocated all your resources that you requested. Now you're good to go if you want to do some sort of IPC. And then firmware can then announce the name service IPC channel, which will initiate the RP message virtio IPC. This is a typical boot flow. So we have a pair of processors. Let's say this is your R5, this is your DSP. And for some use case, your R5 has captured a frame buffer and it wants to pass it to the DSP in a no-copy manner, zero-copy manner. So it just wants to pass over the pointers and do the operation in place. You can see how that works. So each of the processor would have its own RP message implementations. And those are private peripherals. And in the shared peripherals, you would have a DDR, like this is system memory. And it would have some sort of mailbox like for interrupts. So each pair of processors for IPC would have 2 V-rings. So one would be the V-ring that is used as a TX of this processor would be used as a RX of the other processor, and vice versa. Similar concept we have in mailbox. The Q that is used as a TX for this will be used as a RX for this. So the registration happens at device driver probe time. So for example, if you want to pass on this buffer, we take the address, and it has this RP message implementation. It writes some header to that message, which will be used by the RP message implementation in the other core. So this message and the header both is written into the V-ring, which is used as a TX. That V-ring then kicks the associated mailbox queue, which tells that, hey, you have an inbound message in this queue, and then this core would have registered this mailbox as a RX. So whenever there is a message here, mailbox will generate an interrupt to this IRQ controller of the other core. When this core receives an interrupt, it will try to service it, and it will go to the remote proc layers. Then it will ask the virtio framework, do I have any inbound messages for me? Virtio will tell that, okay, you have this message. It will read that message. It has a RP message implementation. Then it will go and strip off. It will basically strip off this header, and the header would contain information like what is the source port, what is the destination port, what channel you sent the message. And based on those information, it will route the appropriate callback for this message. And that callback would then have this address, and so it can read the frame buffer here and do the operation what it wants in place. Similar way, we have the other way communication. Let's say it does some strip off, and then you get this new address. So this writes to the other V-ring that generates a mailbox to the other V-ring, which gives the interrupt to this IRQ controller. Then it reads the data from the other V-ring and then processes it. So this is the round trip data flow of IPC. Okay, now we're coming to the main early boot late attach model here. First, we'll talk about early boot, what we want to do here. Here, this is pretty simple. This is the simplest part. We do just boot the remote processor and its dependent peripherals at the bootloader stage. So for that, obviously, we'll need a rproc driver in your bootloader or ROM, wherever you want to boot it from, which will handle your device reset clocks, anything that needs to start the processor. Then you'll also need to do some firmware processing. So basically, you'll need to read the firmware from your boot media. Then you'll need to do the resource table allocations. At this point, you just need to take care of 2 resources. One is the carveouts. The other is the dev mappings. You don't need to do virtio or trace buffer because obviously IPC master is with Linux, so Linux will do all of that. So in your mappings, what you need to do is you need to map whatever PA to DA the remote processor has requested, and then you'll generate those page tables for the IOMMU if you are using an IOMMU, by the way. And then store those page tables in some reserved memory carve-out, right? And then you pass that address, reserved memory carve-out, into the IOMMU TTB register. TTB is like translation table base, so it just says the peripheral that this is where you have to go and fetch your page tables from. So you program that so that your kernel at the later stage can read this TTB register and know where your page tables are. Then you load the ELF segments into the memory, internal memory, or your DDR, wherever it is there. Then you start the timer that would be needed for your remote processor, and finally you start the remote processor. Typical bootloaders like Qboot have a remoteproc framework to handle all of these functionalities, but if you are doing a custom bootloader, you'll have to do all of this. Now, at the early boot stage, you just need to do everything to use this remote processor as a standalone entity. You don't need to do any IPC or something like that. So at the bootloader stage, your remoteproc can do do its own work while parallel to the HLOS boot. So it can display frame buffers for early splash screen, it can capture frames for early RVC, do an audio, Chime, whatever it needs to do as a standalone entity, it can do that. Now comes the late attach. This is the bit complex part. So here your kernel needs to be smart. Your bootloader can do whatever it wants, just set the rproc to any random state. But your kernel needs to be smart and identify. It cannot just blindly reset the peripheral like in a normal flow. So it needs to identify the correct peripheral state and program it accordingly. So if it's already booted, identify that and then don't reset the peripheral. Attach gracefully into it basically. So this late attach support is spanned across multiple frameworks in kernel, remoteproc, IOMMU, timers, and if you're using any other peripherals for your remoteproc, use that as well. We'll see these frameworks one after the other. We'll start with the remoteproc framework. So the framework for late attach, it expects the implementation, the vendor drivers to set the remoteproc state, because the framework obviously doesn't know how your platform, what is the processor doing in your platform. So if in your vendor code, you need to set the rproc state, and this is your framework code which reads the rproc state. If it is detached, it will call the attach flow. Otherwise, it will call the normal firmware boot flow. And in firmware boot, we do all these things that we already did at U-boot. That is the normal default flow. But we are interested in this attach flow here. Right? So what we do here, we skip all of this loading, parsing part, and we just, the remoteproc framework in this attach flow expects a pointer to the preloaded resource table. Because whenever U-boot or any bootloader would have loaded that rproc, it would have loaded the resource table to some memory as well. So you'll need to save that memory address and then pass it over here so that the kernel can now know where is the resource table, to just register the vert.io and the trace buffers, the other two carveouts that was left from early boot. So there are some challenges also here. In remoteproc framework, how do you go into late attach for vendors? So the first challenge is how do you identify your remote processor state? So different vendors do it different way. NXP, IMX, it hardcodes a set of allowed configurations that your processor can be booted from. There are some platforms which have this IMX rproc none. That means the processor reset is not available from Linux, so it defaults to booting it in attach mode by default. In some platforms, they do have a reset available to be controlled by Linux, so they do a normal boot flow. But this is static at runtime. They hardcode it at the driver level. Whereas some other vendors do have some more flexibility in doing it at runtime. So ST does this by reading a DT property. This is where, this DT property again reads a core register to know the core state. TI does a similar thing. We read the LPAC register of the core to see if it is already turned on, powered on. We skip powering out or resetting it again. Xilinx does a different thing, but it's also interesting. So they check for, the memory carve-out, which is needed for the remote processor, they check the base address of that memory carve-out, and they compare it with a resource table version number, magic number. If those two things match, that means a valid resource table was loaded at the base address of the carve-out. That means someone already booted that remote processor, right? So that's how they identify the rproc state. Second challenge is how do you get the preloaded resource table? So the idea here is to use some sort of stored information from the bootloader or find it in a hard-coded address. Here the vendors have streamlined their methods to a common way. So like NXP, TI, and Xilinx, all of them, the resource table by design is loaded at the base address of the memory carve-out. But Xilinx have in their base address, they have a pointer to where the resource table is stored. Right? So it's pretty much similar. ST does the same thing again. They read a DT property, which reads some register to tell where is your resource table address. And of course, this has to be written by the bootloader, saying that I loaded the resource table at this address. Third and last challenge, how do we establish suspend resume in this late attach mode? So the remoteproc framework supports shutting down both early booted and normal booted rprocs. But the vendors have to decide if suspend to resume is supported in their architecture for early booted rproc. For example, in our case, in TI, we have the concept of a device manager, which is the central entity to do all the reset clock and stuff like that. So they have a concept of host ID. So if your bootloader has turned on the remote processor, the host ID is different for bootloader. And if kernel is trying to shut down the remote processor, the host ID is different. If the host IDs do not match, the device manager just sends a NAC that I'm not going to shut down the remote processor. So in our case, we do not support suspend resume, at least right now, if you boot the remote processor from bootloader. But if it is supported in your case, so what you can do is you can just save the rproc context, get power domains in your attach hook, and you just send a message to your remote processor saying that, hey, you can do whatever you want to relinquish your resources. We're going to turn you off. And then in resume, you boot via rproc firmware boot. Now this is important because earlier you boot via rproc attach, and now you're actually loading the firmware, turning it on everything. So the core is no more attached now. You just treats it like a fresh core that Linux boots. And you do a context restore here. Now let's jump to the next IOMMU framework. So for this, you don't need any changes at the framework level to support late attach, because what you need to do is you allocate a paging domain, and then you attach IOMMU device to the paging domain, which is pretty much common in case you do a early boot or you do a late boot. That is pretty much common. But your implementations have to be intelligent. So what you do is in your attach device hook that this function calls, you'll have to be intelligent and see what is the device state. So for example, this is OMAP IOMMU, and what they do is they check this if it is in a late attached state, it reads the TTB register to get the page tables. Otherwise, if it's a normal boot, it does that. It allocates a paging domain and does all those paging mappings. It sets up this mappings. And it again, for the IOMMU state, it reads some PSC configs to see if it's already powered on or not. Just a note that whenever you're doing, whenever you're prefetching the tables, the mapping sizes could be different, because your bootloader can have a different mapping size. But yeah, that's not a problem. For other peripherals like timer and UART or anything that you want, that your remote processor supports, here you can't actually afford to reset the timer in late attach, right? Because those timers are used as systics in RTOS pretty much for everything, delays, scheduling, all of that. So if you, by any chance, you force configure the timer, your remote processor could crash. So if it's displaying some frame buffers, it will just crash out. So you need to be, again, intelligent here. You need to, what you can do is, this also has no changes at framework level, but at implementation level, what you can do is, you can identify the state, a timer state by reading some counter register to see how many ticks it has counted. And if you see a positive count, you can just see that it is going to the attach mode. So if it is late attach, you can prevent configuring the set source. Basically, you don't assign a clock source to the timer because it is already running, and you don't give it a counter value set load here. So, and these are the common ones, but you need to be careful about other peripherals that your remote processor uses as well. So in summary, if you want to migrate into late attach, or you do not have a remote proc driver, these are the set of things that you need to do to get into late attach. At bootloader, it is very, very simple. You need to write drivers to start all the peripherals and the remote proc, whatever is supported by your platform. Then what you need to do is you just need to save the important configurations into the peripheral registers. For IOMMU, you need to set wherever you have programmed the page tables. For remote processor, maybe you need to set where your resource table is at. So after you have done those things, there's also one thing. So if you're using an IOMMU and you want to store the page tables in some external memory in your DDR, you need to reserve that memory and pass it to the kernel as part of DT fixups, so that the kernel can also reserve that memory. Otherwise, it will just walk over that memory and clear out your page tables, which will again cause inconsistency in your rproc address translations. At kernel level, you need to implement attach operations for all your peripherals. That includes remote processor, timer, and whatever it uses. You can't just force configure anything, right? So this is what you need to do overall as a summary. Now, this is an interesting part. We'll see what are the debugging lessons that we, so this section basically says everything that could go wrong if you're migrating into late attach, right? So if you are selecting some memory carve-out addresses, or you're requesting some carve-outs via your resource table, and how are you gracefully attaching into peripherals. And this is a set of everything that could go wrong when you are migrating into late attach. We'll see that one after the other. So for reference, I was assigned with this exercise to port the late attach patches from 4.19 to 6.1 for TI OMAP platform. So you can just imagine the nightmare I had to go through to even resolve the merge conflicts set aside the functional things. So for this TI OMAP 5 platform, it was an ARM 32-bit platform. It had Cortex-A15 as the general purpose processor and Cortex-M4 as the remote processor as the image processing unit. So it has these two Cortex-M4s used as a lockstep mode, and it had only one cache for both the processors. So it has a unicache interface, and it had two IOMMUs. So one over here near the cache and one over here before your interconnects. So it had to do 2 layers of address translation to access any memory outside. Right, so let's see what happens here. So we started with early boot. That is pretty simple. There was no issues. You boot the remote processor, do anything. There's no problem with that. But the problem came when the kernel, we started booting the kernel. So Linux was not booting with the reserved memory. So when we configured the IOMMU with the page tables, we gave it a reserved memory carve-out of this. And with this reserved memory carve-out, your Linux was not booting. So what was happening was, typically in ARM32 platforms, the boot flow is typically this. This is a bootlin taken from a bootlin blog. So you used a compressed image in ARM32 boot. So you can load the compressed image anywhere in your address, but the compressed image has some bootstrap code which will decompress itself into a specific address. So this is typically governed by your configs. But it is almost the same in every platform unless you specify it differently. So it will start at an offset of 16 MB from your start of RAM. So what happens is wherever you load your compressed kernel, it will always decompress the kernel into this offset, like 16 MB of RAM. So what we were doing is we were reserving this, some part of this, we were reserving this section of the memory for our IOMMU page tables, due to which your kernel was not booting up. So we found this after so much of debug. So you need to be careful where you are placing the carve-outs. You need to ensure that your carve-outs don't overlap with any other system requirements, so that you are good to go with the booting. Okay, so what we did, we changed the carve-outs to some other location at the start of the CMA pool, and with that we were able to get ahead of this problem. So the next problem was we were not able to retrieve the page tables. So the kernel was booting up, and then there was an attach flow in the IOMMU driver. And at that stage, when we were reading the TTB register, it was giving us 0, which should ideally give us some address where your where your pre-programmed page tables are there. When I read that same register through uboot prompt, it was coming at the correct address. Even in the Linux entry point, it was coming as the correct address, but just in the attach operations of the IOMMU driver, it was reading up to 0, which means this peripheral IOMMU was getting reset somewhere in between your kernel init to where your this IOMMU driver was getting probed. So I did whatever we should do. I put a memory watch point on this TTB register, so any writes that was happening to this memory would halt the processor at that stage. And then I got to know there was a platform-specific code, like this OMAP platform-specific code that was happening very early in the boot stage, which was programming all those peripherals into a known configuration state that was off. So if you see, that's the code, and this is where it is basically setting all those logic states to 0, like off. And this was invoked so early in the boot flow, like from kernel init to platform init stuff. So great, maybe you have your late attach related support in your remoteproc drivers or your IOMMU drivers, whatever peripheral drivers, but you need to look at this late attach support as a platform support. You need to look at in the systems view, anything, you need to see what all your platform uses, starting from the kernel init to your driver attach. And anywhere it is doing some assumption that, hey, this is in a good state, I'll just turn it off or I'll just turn it on. There you need to put checks to see, remove that assumption and see the correct state of the peripheral before programming it into any bad state. So yeah, this is the most important lesson here. Next is what was happening was, okay, we got the page tables. So now kernel, the remote processor we were able to attach it to the IOMMU and the rproc, and the attach process was complete, but after this, ideally, the Linux says that I have allocated all your resources and the firmware is good to go to send any RP message announcements or IPC in it. But when I connected to the core, I was seeing that the firmware was stuck in a busy loop. So what it was doing is it was waiting for some address to turn into 7. So if you remember, I talked about the IPC init. Whenever the Linux sets up the resources, it writes the value of 7 into the status bit of your resource table that is present in your shared memory, right? So to eliminate any caching issues, what I did was first I connected the debugger from the application core, and I turned off the MMU to disable the caching, and I read that physical address. It was coming as 7 as expected. But again, from the remote processor, it was not the same address, same value. So what I did was I connected another core from a different core, and I read the same address. It was also coming as 7. That means probably the IOMMU page tables are getting messed up due to why the address translations are incorrect. So the firmware is requesting to read this address, but because the page tables are messed up, it is going into some other garbage value and waiting for this memory to turn into 7, which will never happen because you never know what happens there, right? So it's not reading the correct wherever the resource table is due to some memory page table mess ups. So to eliminate this, I checked out the reserved memory where we put the page tables. I checked the contents, it was all 0. So that's when I got to know that the page tables were getting cleared out, even though it was reserved, but it was getting cleared out. So then I figured out again, I put a memory watch point at that address, write access. And then I got to know there was a DMA alloc coherent that was going on from your remoteproc core to allocate the carveouts. So if you see, that's the code from remoteproc core that issues this DMA alloc coherent. And DMA alloc coherent in its normal flow just clears the allocated buffer. So it is whatever reserved memory you are requesting from the firmware, that is getting allocated at the bootloader stage. But again, at the kernel, it is also doing a DMA alloc coherent, which is clearing whatever you had at that memory locations, which is what we don't want. So to prevent this, what we did was we introduced a non-zeroing flag here in DMA alloc coherent, and we passed over here, and we conditionally did this clear based on that flag, which was helping us with what we needed. So the lesson here is ensure your carveouts are not cleared. Even if you reserve the memory, you need to make sure that that memory is not getting allocated from somewhere else, and that is not clearing out the memories. As a side note, there is some ongoing discussion in the upstream mailing list about whether we should handle these carve-outs resources in the late attach mode in kernel, because carve-out and memory mappings should ideally be done by your bootloader whenever it tries to boot it. And in kernel level, you just need to set up your vert.io device for IPC and trace buffers. So whether or not you actually need this is still in discussion. So probably if you are migrating into late attach after some time, probably will not hit this. Okay, this is the final problem that we had. So here core was unresponsive to IPC. Now with that non-zeroing function, the page tables were not cleared. So this was actually reading it from the correct address now. So it was 7. Now then the firmware was doing its initial RP message init sequence where it was announcing the firmware, the IPC channel where all those ping pongs will be happening. But the channel came up, that's fine. But when we sent a message from the application core to the remote processor in that channel, we did not get a response from the remote processor. And here the situation was so bad that I could not even connect to that remote processor from the debugger, because probably the power or core, the clocks was getting messed up for that core. So I did whatever I could from, verified everything, I verified the IPC stack from the application point of view, like the application core. So I checked the mailbox configurations. I checked whether the remote processor was, registering the correct FIFO interrupts, and whether the mailbox itself was generating an interrupt or not, whether when you write a message. I also checked the vert.io configurations. So whenever I was writing some message in the IPC in the same IPC RP message channel, I was checking if the vert.io TX buffer was getting populated with that message or not, which was the case. It was doing it, but the RX buffer was empty. So the remote processor was not responding here. So then I did whatever I could. What I did was I put a breakpoint. So this was the init sequence of the firmware. And it was, if you can see, there are some debug prints here and here. So it was crashing somewhere in this function. So I put a breakpoint over here before even announcing your RP message channel, and then I stepped through. But it was not much useful. It was just crashing at some random points without doing some random assembly instructions. So it was not really helpful to know what is causing the code to crash, and crash in such a situation that I cannot even read the core register to understand what was the data fault or the instruction fault. It was just, could not even connect to the debugger. So then I came back to two fundamental problems. So if you cannot connect to the connect to the core from a debugger, it means either your power or your clock is messed up for that peripheral, right? So for debugging purposes, I removed all these reset and clock properties from the device tree node for that remote processor. And then I give Linux a free run. And in sysfs, what I did was in runtime, I checked what are the power domain and clock domains that are getting registered. So for power domain, I could not, this was the debug path in the kernel. For power domain, I could not find anything for the IPU, which is your remote processor, which is expected because I removed everything. But in your clock, you can see I think the second last from here, yeah, these ones. These were the IPU1 clock nodes. So this is really concerning because I removed all those properties, but still at runtime, the system was configuring some clocks for that peripheral. So that's when I backtracked that piece of code into the Linux source code, and then I saw that there was a platform driver again, which was configuring some clock properties for that peripheral here. So then it was registering this clocks from here, which was leading to a core crash in the runtime. So the lesson here is you should rely on the system runtime properties only. So no matter what you do in your device tree or statically, you scan it, you see everything is okay. But at runtime, things could go wrong. So always specify things, verify things at the runtime. And a better programming practice in general is to put configurations for one IP at one place, which is device tree is designed for that. That is better. But this was a very legacy platform of TA, and at this time we were still migrating into device tree. So this was a loophole that was just left open, loose end, that we have corrected it now. Yeah. So these are the references. You can see the surround view demo here, and some credits and acknowledgement. I would like to thank these people here who helped me in creating the presentation and the debug as well. Yep, I'm open for any question and answers. Thank you.
If you go back a couple slides to that debug 4.
Yep. Mm-hmm.
On that one, you said that was before you went to device tree?
Right. Yeah, this was before device tree. Yeah. Okay.
So yeah, you said that was before device tree. If, just for future reference, if you try to do that when you move the device, like when you have the clock, actually you probably would hit it before device tree. You might have to boot with clock ignore unused as well, because at least the clocks that Linux knows about, by default, it'll come in and it'll just shut them all down on you on that. So if it knows about that clock, and if no consumer claims it, then it just shuts it off. Just a heads up is all.
Okay. Okay.
On there, just for future reference.
Okay. Yeah. Thank you. Any other questions? Okay. If not, we can wrap up. Thank you. Thanks for your time.